Go. Okay, so we're doing 5.2, a little bit more 5.2 logarithms. So here we go. Find the domain of this log function. So here's the key to this problem. The argument or the input must be positive. You can only take the log of a positive number. It doesn't even matter what the base is. So whatever your argument is, x minus 2, it must be greater than 0. Don't write greater than or equal. It has to be positive. Add 2 to each side and you get x is greater than 2. So that is the domain, or if you want to write it in interval notation, parentheses 2 comma infinity. So as long as x is bigger than 2, this is going to be a positive number. Okay, so this means you can't take the log, if x is equal to 1, it's not going to work because 1 minus 2 is a negative 1. You cannot take the log of a negative number. You cannot take the log of 0. Okay, so numbers 2, 3, 4, and 5 involve properties of logs. So if you have a log of a product, m times n, we're going to write that as log base b of m plus log base b of n. So the log of a product is the same thing as the sum of the logs. Notice the bases have to be the same. The base is b here, where b is some positive number. Okay, if you have a log of a quotient, these parentheses here are optional. I'm going to change pens here. So the log of m over n is going to be log base b of the numerator m minus log base b of n. So the quotient changes to subtraction. Notice these symbols look kind of similar, so that's a good little trick there. Okay, if you have log base b of m to the n power, by properties of logs, the n can come down as a factor. So this is going to equal n times log base b of m. In the old days, these rules were especially useful because without a calculator, isn't it easier to add than multiply, subtract than divide, multiply instead of exponentiate? So these are all proven to be true, these properties. Another property of logs, if you have log base b of 1, it doesn't matter what the base is, the log of 1 is always equal to 0. And here's the proof. If I write this log form into exponential form, this is going to be equivalent to the base to the exponent, b to the 0, and that does always equal 1. So whenever your base b is positive. So I went from log form to exponential form just to show you that this is always true. The log of 1 is always 0. So from log form to exponential form, you write the base. Remember, the log of a number is an exponent, and that's going to equal your input or argument. Okay, so this is what you want to know. Okay, and then finally, to solve this exponential equation, it's not so easy because I can't write 12 as a power of 5 if I could. Like here's a real quick one first. If I say if 2 to the x is equal to 4, solve this equation for x, you could think of it as 2 to the x equals, another name for 4 is 2 squared. If the bases are the same, then all you do is equate the exponents, set the exponents equal. So that would be your answer. And obviously 2 to the second does equal 4, so checkaroo. But here I can't write 12 as a power of 5. So when you have a difficult one like this, not that it's going to be difficult as we're going to see, here's what you do. Just take the log of each side. You could do log base 5, log base 3. I just generally do ln just so I don't have to think about it so much. So take the ln of each side is my advice. And the reason why we do that is so we can make this x more accessible by property of logs, in particular this one here. What am I going to do for this left-hand side? Bring the x down. So x times the natural log of 5 equals the natural log of 12. To get x by itself, divide by ln of 5. So x equals the natural log of 12 over the natural log of 5. That's your final answer. You cannot cancel the ln's and say 12/5. That's totally illegal. ln's always need an input. Logs need an input to make sense. Okay, so that's all. That's all for today. And good luck, everyone.